Good morning. We are going to learn section 4.2. I am hoping to go through both. I'm going to hope to do the entire 4.2 lesson, even though I was going to do part of it on Monday. So if you all run out of time, you'll see the stopping point. Just stop. The assignment is going to be, I think it's just 1 through 10 or something like that. Let me look and see. It's 1 through 11 odd and 14 through 20. But I'm going to go ahead and record the lesson for Monday also. Remember that tomorrow, Friday, is going to be a work day for you to get this assignment done. So that's why you can just watch the whole video until the bell rings, because you're going to have all of Friday to get this work done. So just save the assignment to do in class on Friday. All right, so section 4.2, we're going to learn a couple things, first of which is mean value theorem. Mean value theorem is another theorem that you need to memorize. So this is something that needs to go down your notes. It's got a star by it. It's on the stuff you should know cold. It's actually not here on this first page yet, but you're going to need to know it. So remember that from 4.1, we learned that extreme points happen at critical points, which is where the derivative equals 0 or does not exist, or the endpoints. That's what we worked on in section 4.1. We did it both algebraically and graphically. Now remember from our t-chart that when the derivative is negative, the function is decreasing, and then when the derivative is positive, the function is increasing. We're going to use that information to tell when the graph is increasing, decreasing, decreasing, increasing, and it'll help us decide if it's a maximum or a minimum. I know that some students in some of my classes were saying, how can I tell if it's a local max or a local min? Well, you know that if it changes from increasing to decreasing, it's a max. And if it changes from decreasing to increasing, it must be a min. So that's going to be another way to show you. I'm going to put up that t-chart that we've had on our notes before. You guys cannot see this. Let's see. Okay, so that's the t-chart I was talking about. So remember, where the derivative is negative, we're decreasing. Where the derivative is positive, we're increasing. And if a function is increasing, okay, picture it, it's increasing, and then it changes to decreasing, isn't that going to be a maximum? Yeah. And if it's decreasing, picture it, have it in your head, you're decreasing, oh, now change to increasing. Doesn't that mean you're at a minimum spot? So we're going to use that instead of testing all those points like we did. So the directions here say, find the local extreme values, it should say, and the intervals where the function is increasing or decreasing. So this is a parabola, right? And isn't it a parabola that's opening up, correct? So we know that the function's decreasing, then it hits the vertex, and then it's going to go increasing. So shouldn't it have one minimum at the vertex? Well, let's see the work, the calculus work that could support this. Just like we did before, we're going to set the derivative equal to 0. All right, that's the derivative. Now, where does this derivative equal 0? Doesn't it equal 0 at x equals -1? Okay, so what I'm going to do, instead of before, we would check f of big and f of negative big, and then we'd check f of -1. That's what we were doing before. But we're going to do something different now. So I'm going to erase this. And what we're going to do now is we're going to do a number line. And on this number line is going information about the derivative. So I'm marking my number line as the derivative. This number line is not for f, it's for f prime. And what needs to go on the number line is the zeros of the derivative. Okay, so this is f prime. So when x is -1, f prime is 0. What about when x is over here on the number line? So pick a number over there on the number line, like, I don't know, -2. When you plug in -2 into the derivative, plug -2 into the derivative, 2 times -2 plus 2, wouldn't that be negative? No matter what number you plug into that number line, you're going to get a negative right there. Okay, let's look to the right of -1, right there. Pick a number over there, like 0. When you plug 0 in, or 1 or 2 or 3 or any number into the derivative, you're going to get a positive. So what we have is we've created a number line. We put the zeros on it. We decided which intervals were increasing and decreasing. What this means right here is that this derivative, since the derivative is negative, that means f is increasing. Over here, since the derivative is positive, that means f is increasing. I think I wrote the wrong thing. Let me correct this. Since the derivative is negative, f is decreasing. And now we can answer the questions. So let's answer them. It says, find the extreme values. If the function went from decreasing to increasing, don't we have a minimum? Why do I know it's a minimum? Because if the function went from decreasing to increasing, it's going to be a minimum. So I have a minimum at f of negative 1. Now you know how to find f of negative 1. You just take negative 1 and plug it into f. So negative 1 squared plus 2 times negative 1 minus 3. I'm just plugging it into my function. And we would get 1 minus 2, which is negative 1 minus 3, which is negative 4, I think. Forgive me if I did that wrong. That's our minimum value. Now it also says, where is the function increasing or decreasing? Well, we are decreasing from negative infinity to negative 1. That's where we're decreasing. We're increasing from negative 1 to infinity. Okay, so we've answered the question. Totally based on calculus. But doesn't that make sense based on the fact that it's a parabola that opens up? All right, let's look at this. This is a graph that we don't know what it looks like. So we're going to have to just use our math to answer these questions. So the first thing that we do is we find the derivative. Let's find the derivative. 2x e to the x squared. I used chain rule. And now we want to set the derivative equal to 0 because the extreme values happens at critical points and endpoints. Of course, we don't really have endpoints here. But so where does this equal 0? Wouldn't that be when x equals 0? E to the x squared can never equal 0. 2x can equal 0 at 0. Okay, so we're going to create a number line. Instead of testing those points like we did the other day, we're going to put the derivative on the number line. The number that goes on the number line this time is 0 because that's the 0 of the derivative. Now, this is the derivative. So when we plug numbers in, we're plugging them into the number line because the number line is f prime. So plug in a number like 1 to the derivative. 2 times 1 e to the 1 squared. Wouldn't that be positive? Okay, because the derivative is positive there, we know that f is increasing from 0 to infinity. Okay? All right, let's plug a number in over here like negative 1. 2 times negative 1 e to the negative 1 squared. That's going to be negative. What does that tell us? That f is decreasing from negative infinity to 0. Okay, you notice how I'm using soft brackets. Why don't you guys ask me more about that when I'm back? Just always use soft brackets as a safe bet. The book might use hard, and I can talk about that later. So that's where the function's increasing and decreasing. Now, think about this. If f went from decreasing to increasing, is there a max or a min at 0? Right, minimum. So there's a minimum value at f of 0. Now, to find f of 0, we're not using the derivative. We're actually using f. It's f of 0. So, well, excuse me, it should be g. But g of 0. G of 0 would be e to the 0 squared, which is 1. So that is our minimum because we went from decreasing to increasing. Okay, don't you like this better than section 4.1? I like using the number line instead of testing all the points. I think it makes more sense. Okay, so let's look at one more. 3 to the x to the 4th minus 4x cubed minus 12x squared plus 5. Have you noticed the process? The process is to set the derivative equal to 0, put the zeros on the number line, test the intervals, figure out where the function is increasing and decreasing. That tells you whether or not there's a max or min there. All right, here we go. Derivative. Okay, I'm going to set it equal to 0. All right, that's the derivative. So this time I have more zeros that go on the number line. I have to put 0, I have to put -1, and I have to put 2 on the number line. Now I'm going to cheat a little bit this time. This is the derivative, right? The number line goes to the derivative. It doesn't go to f, it goes to f prime. So isn't that a cube? Doesn't a cube look a little bit like this? Okay, that's the cube. So see how we're negative, positive, negative, positive. Now if you would have tested, if that's bothering you and you're confused about, whoa, what's she doing? I realize that f is an x to the 4th. But this number line goes with f prime. So it's the derivative, which is the x cubed. And that's what an x cubed looks like. So if the number line is the x-axis, and if you tested intervals, you get the same answer, negative, positive, negative, positive. Here's what that tells us. That f, not f prime, f, is decreasing wherever the derivative is negative. So that's negative infinity to -1, and then again 0 to 2. Okay? F is increasing where the derivative is positive. So that's going to be -1 to 0, and then again 2 to infinity. So now let's decide about maxes and mins. Remember that an x to the 4th is going to look like this. That's an x to the 4th, but this number line is the derivative. So let's see. If we went from decreasing to increasing, then isn't this going to be a minimum? Then we went from increasing to decreasing. So we have max and another min. So you notice how we have, this guy isn't going to have, an x to the 4th isn't going to have a maximum. But we still are going to need to use what we did last time in section 4.1 to help us out here. So we need to figure out, since an x to the 4th looks like this, we have no max. But we might have a local max. Remember that this guy right here is going to be a maximum because we changed from increasing to decreasing. So we know that we have a max at f of 0. And what would that be? If I plug in 0, what is that value I just drew on it? It would be 5. So that's a local max. Now we also have a local min. We have some mins going on. And I don't know if it's the absolute min or if it's a local min. And that's going to happen, minimums are going to happen at f of -1 because the function went from decreasing to increasing. And it's also going to happen at f of 2 because the function went from decreasing to increasing. So I'm going to go ahead and take my calculator and I'm going to plug in -1. So that'd be -3 plus 4 minus 12 plus 5. So that's going to be -6 when I plug in -1. And now what happens when I plug in 2? So it'd be 3 times 2 to the 4th. I'm doing this on my calculator right now. 3 times 2 to the 4th minus 4 times 2 cubed minus 12 times 2 squared, which is 4, plus 5. Okay, I get -27. Obviously, which one of those is the absolute min? I didn't hear you. What's the absolute min? Yeah, the -27. So this is the absolute min, which means this is a local min. So for those of you that are wondering, how can you tell whether it's a maximum or a minimum? Go back to the increasing, decreasing thing. If the derivative changes from negative to positive, that means that the function went from decreasing to increasing, which will be a max. No, which will be a min. So think about just the visual of that. Okay, pause if you need to. I'm going to move on. Where is my cursor? There it is. Okay, now the mean value theorem. Here's what the mean value theorem says. The mean value theorem says that if f is differentiable on a closed interval, what does it mean to be differentiable? It means that you can take the derivative there. So it's continuous, there are no corners, cusps, vertical tangents, or points of discontinuity. It's differentiable and it's on a closed interval, then there has to be a value somewhere between a and b where the derivative, f prime of c, equals the average rate of change, f of b minus f of a all over b minus a. So let's think about this. F prime of c is an instantaneous rate of change. F of b minus f of a all over b minus a is the average rate of change. Instantaneous rate of change, average rate of change. The mean value theorem says the instantaneous rate of change has to equal the average rate of change at some point, as long as the function is differentiable and on a closed interval. Now, if you were to multiply both sides of this by b minus a, wouldn't you get this equation? Think about taking that one first box, multiplying both sides by b minus a, wouldn't you get this? Do you realize what this is? This is y minus y1 equals m x minus x1. A and b are x values, f of b and f of a are y values. Holy cow. The mean value theorem is just point slope form rearranged. Now, I'd also like for you to ask me to give you a real life example when I get back of how the average rate of change equals the instantaneous rate of change, and we'll talk about your drive to school, and it will put it in context for you. It makes complete sense. So we're going to look at example 3 on page 187. So open your books. Example 3 on page 187. It says a car is accelerating from 0. If a car is accelerating from 0, takes 8 seconds to go 352 feet, its average velocity for the 8-second interval is given right there. At some point during the acceleration, the theorem says the speedometer must read exactly 30 miles an hour. So this is kind of the example that I want to talk more to you about. I'm going to take it back a notch and tell you that if you guys were to say that you averaged 30 miles an hour on your way to school today, at some point, didn't you have to be going 30 miles an hour? If your average rate of change was 30 miles an hour, your instantaneous rate of change at some point had to be 30 miles an hour. That's kind of like the example of it. I'll talk more about that when I get back. So here's an example of what you might see on your homework. It says, show the function satisfies the mean value theorem on the interval from a to b. So you're going to show that the mean value theorem is true for this equation. And it says figure out where that happens. In other words, where was the instantaneous rate of change equal to the average rate of change? So what I'm going to do, since the mean value theorem uses both the instantaneous rate of change and the average rate of change, I'm going to find both of those. So the instantaneous rate of change would be the derivative, f prime of x. And wouldn't that be 3x squared minus 1 to the 2 power times 2x? Okay? So that's part of the mean value theorem, the instantaneous rate of change. Well, supposedly, according to the mean value theorem, it equals the average rate of change from -2 to 2. So what we need to do here is find f of 2 minus f of -2 all over 2 minus -2. And we're going to figure out where does the instantaneous rate of change, which is this, equal the average rate of change, which is that. So I'm going to do some simplifying and let's see what happens. This becomes, what would f of 2 be? 2 squared is 4, minus 1 is 3, 3 cubed is 27. So minus, isn't f of -2 going to also be 27? Oh, this is so nice. So this is just saying that 6x, x squared minus 1 squared has to equal 0 at some point. So that was nice. It won't always equal 0. We're getting lucky. So where does this equal 0? When 6x equals 0 or when x squared minus 1 squared equals 0? So that's going to be at 0 and at plus and minus 1. So this mean value theorem, there wasn't just one place the average rate of change equaled the instantaneous rate of change. There was actually 3 places where the average rate of change equaled the instantaneous rate of change from -2 to 2. At 0, positive, and -1. So take a minute. Do you see that I used the mean value theorem? I set the instantaneous rate of change equal to the average rate of change. That's what I did to show that the mean value theorem was satisfied. Then I figured out the c. C is just an x value. where that actually happened. When I get back, I'd also like to show you a graph of the mean value theorem so you can kind of see what it is that's going on. So there you go. There's your assignment that we're going to work on for sure on Friday. So if there's time, I would like for you to keep this tape rolling. Keep this rolling, and I'm going to go ahead and do the notes from Monday because it'll be like a blended learning lesson or a flipped lesson. We can just have more work time in class on Monday. It'll give us more time for me to answer questions on Monday. If you have time today, I would prefer for you to just go ahead and keep letting this play. So I'm going to keep going. If you don't, stop it, and this will be your assignment for Friday. All right, so I am going to keep this a-rolling. And this is a little lesson. We're also going to learn about antiderivatives, which is really what our focus will be on for the second semester. But we're going to take a sneak peek at it in this section. Antiderivative. You've heard me mention this word already. An antiderivative of a function is a function f that satisfies f prime equals f. So here's what we're using. We're using this capital F. So if instead we started with f and we took the derivative, we would get lowercase f. If we were to take the derivative again, we would get f prime. If we were to take the derivative again, we were to get f prime prime, and we could keep going and going. So do you see how I'm using a capital F just to denote antiderivative instead? That's what we're going to do to note it. Now, if I should have used capital F, if capital F is an antiderivative of lowercase f, so if capital F is the antiderivative of f, then there are infinitely many antiderivatives that can satisfy it because we could add constants, which would give them the same derivatives. What that means is that if we have a function like x squared, its derivative is 2x, right? How about x squared plus 3? What's its derivative? 2x. How about x squared minus 7? What's its derivative? 2x. Do you see how there can be as many constants as possible that would give you the same derivative? So when we're taking the antiderivative, we don't know what that constant is. Well, sometimes we'll be able to. And so whenever we take the antiderivative, we put a plus c on there, and that's telling us, hey, there could be some constant on there. It could be any constant. So we're going to do two examples. It says find all the possible functions with the given derivative. So what would give us a derivative of x squared? So what gave us a derivative of x squared? We know that capital F would have to be an x cubed, right? Because when we take a derivative, we come down a power. But the problem with this is that if we were to take the derivative of x cubed, what would we get? What? What would we get if we took the derivative of x cubed? Yeah, 3x squared. Well, we don't want a 3 there. We just want an x squared there. So what we can do is this. What about if we divide by 3? What would the derivative of x cubed divided by 3 be? 3x cubed divided by 3, which would give us an x squared. And now we need to put a plus c on here. You can always check yourself. Take the derivative of f, and we should get lowercase f. What would f prime's derivative be? In other words, the derivative of 1/3 x cubed plus c. Its derivative would be 3/3 x squared plus 0. And isn't that actually f? Then we did a good job. Normally when we take the derivative, we come down a power and we multiply by that number, right? So if we take the antiderivative, we're going up a power and we're dividing by that number. Instead of coming down a power and multiplying, we go up a power and divide. All right, trig doesn't work the same. So you're just going to have to think about this. Turn your brains on. Think through those note cards and all that memorizing of the derivatives you did. What function gave us a derivative of tan x secant x or secant x tan x? Do you remember? Somebody remembers. Whoops. What gave us a derivative of secant tangent? That's right. Secant of x. Wasn't secant of x's derivative secant tangent? We just need to put the plus c on there. So we're taking antiderivatives. Oh my gosh, it's so exciting. I know, that wasn't very much excitement in my voice, was it? So you're working backwards on the differentiation rules. If you know just one point, you can actually figure out what the c is. So I'm going to take this another step here. If instead of just saying, find the function who gives us the derivative, they give us this initial condition. This is considered an initial condition, or a condition on the graph. So what we want to do is we want to find the antiderivative, which we already did. We know it's x cubed divided by 3 plus c. Okay, we did that example already. We're going to use the fact that when x is 1, y is 1 to figure out what c is. When x is 1, see how I let x be 1? Y is also 1. And now we can solve. And now that we know what c is, we have a better answer for f of x. F of x doesn't just equal x cubed over 3 plus c, it equals x cubed over 3 plus 2/3. Like, we're able to figure out what the c is if they give us an initial condition. One more example. We'll do a trig one. It still wants us to find the antiderivative, but then it wants us to actually figure out what the c is because it gave us an initial condition. We know that the antiderivative is secant of x plus c. But we know when x is 0, y is 3. So y is 3 when x is 0. What is the secant of 0? Let's see, think about the graph. That would be 1. And so here, c is 2. Our job isn't to find c. Our job is to find f of x. So f of x equals secant of x, not plus c, but plus, what do we find our c to be? 2. Now, I was talking about capital F, but keep in mind that they could word it differently. Here, they said instead, given the derivative, find the function. Isn't that also working backwards? That's the same as saying, given f, find capital F. It's just choosing different ones. I could say, given the second derivative, find the first derivative. Isn't that working backwards? So it's just different notation. I'm not sure how many different ways the book will ask you, but that's what we'll be working on Monday, okay? And if you have time, you can, if you get through 1 through 10, 11 odd, and 11 through 14, whatever it is, you can start on this, but we'll be working on this on Monday. I hope you have a wonderful day and a wonderful weekend.